work with metal every day. We weld it, cut it, grind it, and machine it. Most of the tools we use are made of metals that are chosen for toughness and strength. And most of the machines we work on are made of metal, metal chosen for its strength and toughness, as well as for many other properties. You need to know something about these properties in order to be able to choose the right tool for a job, to determine the speed at which a metal can be cut, and to help diagnose equipment problems. To do all this, you need to understand how a metal's properties affect its workability, weldability, and machinability. The answers are revealed through metallurgy. Metallurgy is the subject that defines what metal is and describes metals by a certain set of properties. In this program, you'll learn about different types of metals and how to identify each one. We're going to look at metals and see what their different properties are. We'll also discover how these properties can be altered. And we'll find out something about metal failures and what can be done to prevent them. Metals all share certain common characteristics, although different metals can have properties that are very different. Mercury, for example, is a liquid at normal temperatures, while iron is a solid, but both are metals. According to the dictionary, a metal is a substance that is a good conductor of electricity and a good conductor of heat. As you know, if you've ever picked up a hot skillet, this one is not hot. It's opaque, meaning that you can't see through it. It's lustrous, meaning that it can be polished to a shine, although it takes several hours to do this one. Fusible, which just means you can join it together by melting it and letting it harden. And ductile. Ductile means it can be worked to change its shape without breaking. Metals all share these general characteristics to a degree, each in accordance with its different properties. Metals can be mixed together as alloys, producing properties that can be different from the basic ingredients. Copper and zinc can be mixed to form brass, for example. Brass is tougher and stronger than either copper or zinc. Okay, now let's talk about the different physical properties metals possess. Tensile strength, compressive strength, and shear strength are all properties metals have to some degree. Plasticity is another common property. Malleability and ductility refer to plasticity. Metals can also be described by their brittleness, toughness, hardness, and by their resistance to fatigue, to corrosion, and to heat. Now, in order to understand what these terms mean, it's important to know something about stress and strain. Stress is the result of any force, even the force of gravity, that acts on a material. When a force is applied, stress is distributed all through the material. For example, the weight of this bar is causing stress within it. Now, if we increase the load by applying some external force, stress is increased throughout the bar. If we add enough of a load, we begin to cause the bar to strain by bending. Strain is the amount a material is deformed when it's under stress. The amount the bar bends is the amount of strain caused by a certain load. A metal's strength is its ability to withstand strain from the force of a load. Strength is one of a metal's most important properties. The ultimate strength of a metal is the maximum amount of stress it can take from a load before it fails. There are three common ways of describing a metal's strength. Tensile strength is the most common one of these. Tensile strength refers to the ability of a metal to resist being pulled apart. A metal's compressive strength is its ability to resist being deformed under pressure. And shear strength refers to resistance of crossways stress. Plasticity is the second important property of metals that we named. Plasticity is the ability to resist failing when it's being deformed. Plastic deformation is a permanent change in shape. This modeling clay is a good example of plasticity. It can easily be molded and stretched without breaking up. Now, we talk of plasticity in metals in two ways. One is ductility. A ductile metal is a metal that can be stretched out to a thin shape without pulling apart. You take this copper wire, for example. Copper wire is formed by drawing the metal through a series of dies to produce fine strands from thicker rod. Ductility is deformation under tension. The other way we refer to plasticity is malleability. Malleability is plasticity under compression. A malleable metal can be hammered or forged into shape. For example, tools and other items of high strength are frequently forged. A metal has to be malleable to be forged. And usually, if a metal is malleable, it's ductile too. I say usually, but not always. And one exception is lead. Lead is very malleable, even at room temperature. However, lead is not very ductile at all. You pull it, and it breaks apart. Well, that is, if you pull it hard enough. The third property of metal that we mentioned was brittleness. Brittleness is the opposite of plasticity. A brittle metal is one that will break suddenly without deforming. Brittle metals often fail without warning. No visible sign of stress is apparent until actual failure occurs. Brittleness is a natural property of some metals, but in others it's a property that only shows up if the metal is produced in certain ways. Cast iron, for example, is fairly brittle. Two properties that go hand in hand are toughness and hardness, but they shouldn't be confused with each other. A tough metal will stand up to shock and repeated stress without failing. It can be deformed without breaking and still keep most of its strength. Spring steel is a tough metal. A hard metal is one that withstands indentation from another object. Ordinarily, the harder a metal is, the stronger it is. Hard metals resist being cut and resist abrasive wear. Also, a hard metal is usually more brittle than a soft one. This file, made of tool steel, is a good example of hard metal. It's very, very strong, and it's remarkably brittle. Let me show you what I mean. Now that's brittle. Although toughness and hardness are distinct properties, a tough metal is often a hard metal too. Steel and iron are both tougher and harder than, say, copper, and copper is tougher and harder than lead. The tougher and harder a metal is, the more difficult it is to cut. Toughness determines how easily a metal can be cut. Hardness determines how fast a metal can be cut. Oddly enough, heat treatment that affects one usually affects the other in the opposite way. Hardening iron or steel, for example, reduces its relative toughness. Tempering the same metal to bring back its toughness also reduces its hardness and strength. I'll show you what I mean in more detail in a later segment of this program. A metal's resistance to fatigue, corrosion, and heat are also important properties. The tubes of a boiler are subject to fatigue failures. Fatigue occurs when a metal is stressed over and over again. Vibration fatigues the metal and can cause failure. Heat fatigue comes from stresses of alternately heating then cooling a metal. Corrosion is the result of chemical action on a metal. Corrosion is where the metal is eaten away by another substance. Acids are corrosive. Some metals are very resistant to corrosion, however. Stainless steels are good examples of corrosion-resistant alloys. Stainless steels are produced by alloying steel with nickel and chromium, which are both highly resistant to corrosion. Nickel and chromium are also used in plating other metals to resist the effects of corrosion. Finally, heat affects the properties of metals. At high temperatures, metals are weaker, softer, not as tough. A heat-resistant metal is a metal that keeps its strength at high temperatures. This drill bit, made of high-speed tool steel, is a good example of a heat-resistant metal. It keeps its strength and holds a sharp edge so it can cut other metals, even at very high temperatures. Now, all the properties we've mentioned combine to give a metal certain characteristics. They determine how easily a metal can be worked. They determine how fast a metal can be machined and what tools we must use. And they also determine how easily a metal can be welded and what welding method is necessary. These characteristics, workability, machinability, and weldability, are not true properties in themselves. Instead, they are the result of a combination of strength, toughness, hardness, plasticity, and so on. Knowing what the properties of a particular metal are will give you a pretty good idea of how you can use it and form it. There are also ways of changing the properties of metals so you can get it to do the necessary job, and one of these is heat treatment. Many times it'll be desirable to heat treat a metal to make it easier to work on or machine. We've also said already that heat treatment can be used to strengthen and toughen metals. This is so important to a mechanic that we'll devote an entire section to heat treatment later in this program. Finally, working a metal either hot or cold can be used to improve such desirable properties as toughness and strength. Now, so far in this program, we've examined why metallurgy is useful to mechanics, and we found out what metals are and what properties they share. Finally, we've seen two things we can do in the shop to make metals easier to work with or to improve certain qualities of metals. I want you to pause now to read through the material in the text and answer the questions. When we return, we'll look at what kinds of metals there are and what makes each one special. In the last segment, we looked at the properties and characteristics that all metals share. But there is one metal, iron, that has a very unique property the others don't share. And that property is magnetism. Magnetism and the effects of magnetism are so important that without it, we'd be in the dark ages again. We rely on magnetism to be able to generate electricity to light our plants and our homes, provide power to heat, cook, even run our transportation. Because this property is so important, and because of the range of its other properties, iron is the basis for a whole classification of metal and alloys. It's called ferrous metals. Ferrous metals are any metals whose major element is iron. All the many kinds of steels are ferrous metals. On the other hand, copper, brass, aluminum, and lead are examples of non-ferrous metals. Non-ferrous metals are all metals whose primary element is a metal other than iron. All ferrous metals begin as iron ore that's taken from the ground. The ore is converted to metal in a blast furnace. The metal that comes from the blast furnace is drawn into molds made of sand called pig molds. The pig iron is about 93% pure. The rest is carbon and other impurities. Pig iron is the most basic form of ferrous metal and is the basic ingredient for cast iron, wrought iron, and steel. Cast iron is the next step in the refining process. Pig iron is tossed into the furnace along with scrap iron. Further impurities are removed, and the grade of cast iron that results depends on the degree of refining and the amount of scrap used. Cast iron has remarkable compressive strength. That's why it's great for things like bridge supports. Cast iron's resistance to corrosion and fatigue help make it ideal for foundation structures and supports as well. And cast iron is also used to manufacture internal combustion engines for cars and buses, trains, and industry. Wrought iron is the next step in the refining process. Wrought iron is very pure, with only controlled traces of carbon remaining. Part of the wrought iron manufacturing process is the rolling mill, which works the white-hot metal to make the structure of the metal tougher and more uniform. Wrought iron is also corrosion and fatigue resistant. It is widely used for low-pressure piping and for fasteners such as rivets and nails. The ultimate step in the refining of iron is the conversion of iron to steel. By using extremely high temperatures, the physical structure of the iron changes into what we call steel. During the conversion process, virtually all the impurities are chemically removed. What's interesting is that the metal resulting from the steel-making process is so pure that small amounts of carbon and traces of other impurities have to actually be put back into it again to further improve certain of its properties. Now, how much you put back in makes a big difference in the kind of steel you end up with. Plain steels are identified by the amount of carbon they contain. Mild steel, for example, which is easily machined and used for non-critical machine parts and hardware such as low-grade washers, nuts, and bolts, is a low-carbon steel containing less than 1/3 of 1% carbon. But this pump shaft is made of a medium carbon steel. Medium carbon steel contains somewhere between 1/3 and a little over 0.5% of carbon. It's a lot stronger than mild steel. Medium carbon steel is often used for heat-treated machinery parts like this. Hand tools and cutting tools, on the other hand, are usually made of high carbon steel. High carbon steel has from 2/3 to over 1% of carbon. It's a very hard steel that's also used for a lot of machine parts like cams and crankshafts. You can see from these examples that plain steels have a tremendous number of uses. But if plain steel won't do the job, it can be improved by alloying it with different elements. Alloy steels come in many types. One of the most common types, of course, is stainless steel. Stainless steel is properly called corrosion-resistant steel and actually refers to a whole family of chromium and chromium nickel alloy steels. The chromium and nickel make the steel resistant to corrosion and scale and to attack by acid. Now, the shell of this tank is made from another alloy steel, nickel steel. Nickel steel has enormous strength and toughness and is often used for armor plate. Then we have vanadium steel. Vanadium steel is used for gears, axles, crankshafts, any place where machine parts require high strength and fatigue resistance. This valve body is made of carbon molybdenum steel. It's a very tough steel, and it's also used for steam fittings and boiler plate. And the high-speed steel of this drill bit is part of a family of tool steels. These steels can be used for cutting at very high speeds and temperatures. They are made of different quantities of tungsten, chromium, and vanadium. Sometimes they also contain molybdenum. Without iron and steel, the ferrous metals and their alloys, our world would be very different. The strength of ferrous metals allows us to build structures for living and working and moving from place to place. And the toughness and hardness of ferrous metals lets us create tools to work on other metals that are also tough and hard and strong. In this part of the program, you've seen that there are two classifications of metals, ferrous and non-ferrous. We've talked about how different ferrous metals are produced and how they're used. We've also seen some typical applications of ferrous metals and learned how their properties suit each use. Ferrous metals are very important to all of us, but non-ferrous metals are just as important in many other ways. In the next part of our program, I'll show you why. But before continuing, read section 2 of your text and answer the questions. In the last part of the program, I talked about ferrous metals and showed you how much our modern-day lives rely on these metals and their properties. But it's equally true to say that without non-ferrous metals and their properties, things would also quickly grind to a halt. You see, these metals have some very desirable properties that iron and steel just don't have to the same degree. The non-ferrous metals you will probably find around your shop or plant include copper, lead, aluminum, and zinc. You'll probably also find yourself working with alloys such as brass, bronze, and nickel copper. Let's take a look at these one at a time. Copper is used for electrical wiring. because it is second only to silver as a conductor of electricity. Copper is probably the most abundant non-ferrous metal you'll run into. Copper is also used for piping because it is corrosion resistant, especially to salt water corrosion. Another typical use of copper is for gaskets. Because copper is a very malleable metal as well as ductile, it will compress to form a tight seal when it's used this way. You'll also find copper hiding around the shop in alloys such as bronze, brass, and copper-nickel and nickel-copper. Another non-ferrous metal you'll see used in many places throughout the plant is zinc. Zinc is used as a protective coating because it is highly resistant to corrosion. Zinc is the protective element in galvanized metal applications, such as ventilation ducting. Pure zinc is used to protect the metals in some heat exchangers because it is highly subject to the electrolytic action of salt water or brackish water that flows between dissimilar metals. This is called a sacrificial zinc or sacrificial anode because the plate of zinc will decompose fairly quickly. However, it will tremendously reduce the rate of attack on the materials that make up the heat exchanger. And another non-ferrous metal you'll work with is lead. Lead is extremely dense. As a matter of fact, 1 cubic foot of lead would weigh about 700 pounds, or about 320 kilograms. Lead is fairly common, but its uses are limited. Lead is used in sheet form as shielding against radiation in radiographic testing and radiology. Lead is also used as an alloying element in soft solder, probably one of its most common uses. Now, over on the other end of the scale, literally, is aluminum. Aluminum is very light in weight. It can be alloyed and used in castings to produce cases for transmissions, gear drives, and speed reducers. Aluminum is also used in automotive and aircraft engines, as well as aircraft construction because of its light weight. Aluminum is even used in heat exchangers, such as the radiators that go into air conditioners. Like aluminum, nickel and tin are not usually used in pure form, but are used in alloys. Both nickel and tin alloy with copper to produce alloys superior in strength and corrosion resistance. Tin is also alloyed with lead to make soft solder. Both nickel and tin are very resistant to corrosion, and both are used as plating metals to protect other base metals. Another typical non-ferrous alloy in common use is brass. This brass sheet is used as shim stock because it's tough and hard but cuts fairly easily. True brass is an alloy of copper and zinc. Many other alloying ingredients can be added to improve certain of its properties. Complex brass alloys include ingredients such as lead, tin, aluminum, iron, or other elements. Bronze is another copper alloy. Bronze was originally an alloy of copper and tin, although complex bronze alloys have been developed, much like alloys of brass have become common. Nowadays, there is no really clear distinction between brass and bronze. For example, commercial bronze that is used for hinges and other kinds of hardware is really a low alloy brass made of copper with less than 10% zinc. Copper-nickel and nickel-copper alloys both have very high resistance to corrosion. Copper-nickel, which has more copper than nickel in it, can be worked pretty much like copper. Nickel-copper alloys have more nickel, and they're stronger and harder than either of their parent metals. In fact, where corrosion resistance is of major importance, nickel-copper alloys can take the place of steel. One of the most widely known nickel-copper alloys is actually a sort of natural alloy. This is Monel, a mix of about 2/3 nickel and 1/3 copper. This is the mix that exists in the ore when the metals are mined, and it remains in this ratio through the refining process. Small amounts of iron, manganese, silicon, and cobalt make up the remainder of the alloy. K-Monel is another version of the same alloy, but the addition of aluminum to the alloy makes it even harder and stronger. From all this, you can see that the many non-ferrous metals and their alloys are needed to provide valuable properties in many different applications. Some are used for a very narrow range of properties. Others seem almost to share the versatility of iron and steel. In either case, it's important to know what you're working with and the properties you can expect of the metal. In the next segment of the program, we're going to look at how metals are identified. I'll show you how they're classified, and we'll look at the systems of marking metal stock so it can be readily identified. We'll also see how to identify unknown metals by their basic characteristics and the way they react chemically and physically to certain treatment. Before going on, though, read Section 3 of your workbook and do the exercises. If you have any questions up to this point, ask your instructor to clear them up before you go on. As we've seen up to this point, the properties of different metals vary widely. In order to know how to work with a particular piece of stock, it's important to be able to tell what it is. For instance, if you need to turn a shaft from a piece of stock, you've got to know what you're working on to choose the appropriate turning speed, cutting depth, and feed. Also, it's helpful to be able to choose the correct tool. For another example, if you have to fabricate a weldment, you've got to be able to choose the right technique, the right rod or filler, and what heat flame or what current and speed to use in welding the piece. Now, for metal stock, bars, rods, shapes, and sheet, there are standard methods of identification. In this part of the program, we're going to explore the standard designations of ferrous and non-ferrous metals and the marking systems for raw stock. Then we'll take a look at how you can rapidly identify the characteristics of an unknown sample of metal and figure out pretty accurately exactly what you've got to work with. Let's start with the standard designations for the different metals. Ferrous metals are all identified by a code that indicates the composition of the metal. Two systems are used. One is known as the SAE system. SAE stands for the Society of Automotive Engineers. The other is the system designed by the American Iron and Steel Institute, or AISI for short. Now, both systems are the same, except the AISI system uses a prefix to show how the steel is made. Here we're going to show just a few examples. Complete details of these systems are given in your text. Both systems use a 4 or 5-digit number to indicate the composition of the steel. If there is an AISI prefix, it just tells you the basic steel-making process for that stock. The first 2 digits tell what type of steel. In our example, the 1 indicates plain carbon steel, and the 0 tells you that there is no important alloying ingredient. The last 2 or 3 digits indicate the carbon content. This example shows 0.20%, 1/5 of 1%. So 1020 or 1020 steel is low carbon plain steel or mild steel. If the carbon content were over 1%, a 5th digit would be added. Say 100 means an average carbon content of 1.0%. This would be a high carbon plain steel. The system used for aluminum is somewhat similar. Your textbook goes into much further detail on these and the other systems, but this ought to give you a basic understanding of how these systems work. The system for aluminum uses a 4-digit system to tell the relative purity of the aluminum and the alloying ingredients. A system of letter suffixes tells how the metal is heat treated. Other non-ferrous alloys are usually simply identified by the percentages of the major alloying ingredients. For example, a copper-nickel alloy might be identified as 70-30 copper-nickel. Cu is the chemical symbol for copper. Ni is the symbol for nickel. So there's 70% copper and 30% nickel in this alloy. Some non-ferrous alloys are known by their trade names. Monel is one example we've already seen. Now, this sheet of brass we've got is a good example of how stock is marked so you can tell just what you're working with. It's called continuous identification marking, and it conforms to a federal standard that calls for the manufacturer's name or trademark and the commercial identification of the metal. The continuous identification marking system replaces the old system of color-coding raw stock. But you'll find some examples like these around, so it's helpful to have some idea of their meaning. Your text has a more detailed description of this system, but basically it goes like this. Each color represents a number, and that number is part of the standard designation system we saw earlier. Simple, no? Well, maybe not, but a little understanding goes a long way towards preventing confusion, and practical experience will make things even easier. Of course, not every piece of raw stock is going to be marked. Stock that's been around for a while may be missing those sections that were originally marked. Many of the base metals you work with can be identified by their color, texture, and weight. Iron, copper, lead, and aluminum are all pretty easily distinguished this way. However, many alloys look a lot like each other, or like the parent metals, so that they're hard to tell apart. How do you find out what you got? Well, for less critical needs, you can use 4 or 5 different tests to get a good idea of what you're working with. However, none of these tests are perfect, and it's never wise to settle for the results of one of them alone. But a combination of these should give you enough evidence to decide fairly accurately what alloy you're working with. Now, if the application is really critical, then you've got to look up specs and get the right stock from a known source. You might have to get your supervisor to give you the info you need and even special order the material. Let's say, for example, that you need to turn a new shaft for a pump and you want to know what metal to use. Well, you might have a piece of stock that isn't marked and you want to know if it's okay. The tests are simple. You can use a magnet to identify some ferrous metals and tell whether a piece of steel is plain steel or an alloy. Plain steel will react to a magnet. Look at that. Now, stainless steel usually won't because of the percentage of other metals in the alloy. Or, if there's any response, it'll be very, very weak, if at all. Another test is the chip test. Chuck your sample in a lathe and take a light cut on it. The example we're seeing is stainless steel. Note the way the long curls form from a 10,000ths cut. All right, now let's try another piece. Uh-oh, obviously this one won't do the job. It's some sort of mild steel. You can tell it's mild steel by the shorter curls and chips. Although from the color we can tell our third example is obviously not the stainless steel we want, it'll show you how differently a non-ferrous alloy cuts. This sample is brass. There's a chart in your text that will give examples of results of this test and the others for all the metals you're most likely to be working with. Our third test is the spark test. It's a common test that's used on ferrous metals because different ferrous metals give off a shower of sparks that'll help you identify them. It's not used on non-ferrous metals because non-ferrous metals don't throw off a stream of sparks. In a spark test, you compare the color, size, and shape of the spark stream from a known sample with the stream from the stock you're trying to identify. What a spark test will tell you is something about the hardness, the carbon content, and the alloying of a ferrous metal. For instance, you can tell relative carbon content by the length of the spark stream. Generally, a high carbon steel will have a longer stream than, say, low carbon mild steel or iron. Remember that each time you use a new piece, you need to dress the grinding wheel, so residue from the previous test piece won't confuse your findings. Also, you've got to be careful to apply the same pressure to each sample. Here's an unknown sample we're trying to identify. It gives off a white-orange stream that's long and full. Now let's try a sample that's known. We dress the wheel so the residue from the previous test won't confuse our findings. This sample is stainless steel. It's an alloy steel that has a relatively low carbon content. We can see the spark stream is much shorter and very light, so we'll need to try another known sample. Again, we dress the wheel. We know this sample is a high carbon plain steel. This spark pattern is long and full, a lot like our unknown sample. To be sure, let's look at that one again. Dress the wheel. And here comes our unknown sample again. And there you have it. This steel is pretty much like our known sample of high carbon plain steel. The longer spark pattern shows it's harder and has a high carbon content. The abundance of sparklers in the stream of sparks is an indication of carbon content. The higher the carbon content, the more of these there are. Carbon in the metal causes the glowing particles to explode, creating these sparklers or chicken feet. Another test we can try is the acid test. This test uses nitric acid that's very pure to help identify different metals and alloys. In some plants, you may have to rely on the chemistry lab to do this test for you. If you do it yourself, though, you need to carefully observe the same kind of safety precautions they do. Skin and eye protection are very important here. Place a few drops of acid on a sample piece of metal and watch for a reaction. The example we're trying is stainless steel. After 2 minutes, if nothing has happened, a drop of water is added to see if any reaction occurs. A little more water is added, 1 drop at a time. We can see a little heat reaction caused by the water mixing with the acid, but still no reaction with the metal. This is because stainless steel is very resistant to corrosion. After 5 minutes, you can be pretty sure nothing else is going to happen. Let's see what happens to a plain steel. Place a few drops of acid on this sheet stock and look for a reaction. With just the acid, nothing happens, which might lead us to believe that this is a corrosion-resistant steel. But then we add just 1 drop of water. At first, we see a little heat reaction, but nothing more. Now there's an obvious reaction, and a strong one. That's definitely not stainless steel. Some metals react immediately to the acid alone. This sample of brass shows how vigorously the reaction takes place. The greenish color is one indication of the copper in the alloy. Copper itself shows the same color, but leaves a different residue. Other tests will give you an indication of some properties of a sample. Testing with a file will let you compare one sample with another to see if they're similar in toughness and hardness. Hardness can also be compared by peening the samples. But remember, these tests aren't really very precise. They'll only give you a general indication. It will take a certain amount of experience to be able to perform these tests with confidence in your results, but when you've done them a number of times, you'll find you have a pretty good eye for what you're looking for. Of course, not all of these tests are always practical, and in a well-run shop you may seldom need to identify an unknown sample out of stock. But from time to time you'll need to know how hard a piece is, or if the piece you're trying to duplicate is a particular kind of alloy, and that's where these tests come in really handy. Always remember the necessary safety precautions for each type of related shop work, and be especially careful when you're handling acid. With a little practice, all this will come naturally. I want you to pause now to go through section 4 of your text. It contains a world of information on identifying the metals you'll routinely work with. Answer questions in the text, and make sure to clear up any questions you may have with your instructor. When we come back, it'll be time to find out how to make a metal do what you want it to do. Now that we've got a good idea of how to identify a metal we want to work with, it's time to find out a little about how we can control the properties of the metal. Heat treatment is one way we can do this. In fact, once the metal comes from the manufacturer, heat treatment and working of metals are the only ways we can improve the properties to make them do the jobs we need done. In this part of the program, we'll see what heat treatment can do, and we'll also see how hot working can help us do our job easier and quicker. Basically, there are 3 ways heat treatment is used to affect the properties of a metal. Heat treatment can be used to harden metals. Heat treatment can be used to temper metals, making them tougher and more fatigue resistant. And heat treatment can be used to soften a metal and make it easier to work with or to machine. This last kind of heat treatment can also be used to assure uniformity of strength and relieve internal stresses. In order to find out how all this is done, we'll start out with 4 pins, just like this one, that were cut from mild steel stock. Mild steel is fairly malleable and not too hard. We can try a couple of tests to demonstrate the properties of our samples. To see how hard these pieces are, we'll go into the lab and use this machine to test one's hardness. Since hardness is a metal's ability to resist indentation, what we're doing with this test is finding out how much the surface of the piece is indented by a very hard material. This hardness tester uses a certain known pressure to force the hard stylus into the sample surface. The dial indicates hardness based on the amount the stylus penetrates the surface. Our untreated sample reads 72 on the scale. This reading is typical of mild steel that's untreated. To see how malleable the untreated piece is, we clamp it in a vise and hammer it until it bends. It didn't take very much effort at all to bend it over 90 degrees. Now that we've seen how soft and malleable an untreated piece is, we're going to see what heat treatment does to the rest. Let's take a look at one typical example of how hardness and strength can be controlled in a metal. If we heat the remaining 3 pins on the hearth until they're nearly white hot, and then take them and quench them really fast in cold water, their hardness and strength should be improved a lot. But if we clamp one in the vise and try to get it to bend, we see that the pin has become very brittle and cannot withstand the hammering stress. It's not very tough. If we check the hardness of the piece we just broke, though, we find it's 99.5 on the scale. A lot harder. So hardening will cause the metal to get brittle. If we need a piece to be tougher and less brittle, then tempering will do the job. We'll heat the pins again, this time to a somewhat lower temperature. For the purpose of this demonstration, we don't have to be too precise. Our Ford Smith can tell pretty much by the color of the metal when it's ready to come out for each of these steps. In production heat treating, an oven that can be very precisely controlled is used to yield exactly the properties being sought. Again, we quench the pieces, this time from a lot lower temperature. And when they're cool enough to handle, we try one in the vise. This time the piece is beaten and beaten again, but it doesn't break. And it's so tough that it bends very little. Now, if we chuck the tempered piece in the hardness tester and try its hardness, we see that it's lost some of its hardness. This one reads 92.5, but we know the sample is very tough. Now, what if we have a piece that's been tempered like this, but we need to work it? It's too hard to work easily, and we know it's too tough to bend easily. Well, annealing can soften a metal and make it easier to work with. Let's see how closely we can return this to its untreated state by annealing. With the pin heated again, we're going to let it cool slowly in the air. Cooling it like this makes all the difference. After it's cooled down, we'll find it's a lot less tough and it's almost as malleable as it was originally. It can be bent over almost as easily as an untreated pin. If we try it for hardness, we see that it's nearly back to its original hardness. It's back down to 75.5 on the scale. Now that we've seen what annealing did to this pin, let's look at a typical example of the use of annealing in the shop to make metal easier to work with. This sheet of copper is used as gasket material. A pattern has been laid out, and it has to be cut to size. Without annealing, this would be a hard cut to make. After the piece is annealed, though, it can be done rather easily. In order to know when the metal is hot enough for our purpose, a marking crayon of temperature-sensitive material is used. When the marks on the material melt, the temperature we want has been reached. Copper can be annealed at a temperature as low as 500 degrees Fahrenheit or 260 degrees centigrade. By heating this sheet with a torch to a uniform heat, and then quenching the workpiece rapidly in water, we've softened up the metal so it can be cut fairly easily. Annealing copper not only makes it easier to work with, but makes it ideal as a gasket material. And that's because it's not only become soft, it's become very compressible. And it can be used over and over again just by annealing each time before it's reused. The process of annealing works to relieve internal stresses caused by the localized heating from welding. After a weldment is completed, the part is annealed to prevent these stresses from later causing failure of the weld or the metal itself. Now, in order to demonstrate what heat treatment does to the strength of the metal, we've got to make some very precise test specimens and give them to a lab with a machine that will accurately test their strength. This machine tests the tensile strength of the samples by pulling them until they yield. Our first sample has been thoroughly hardened. It was heated to a very high temperature and then was quenched rapidly. And as the piece is pulled with greater and greater force, we don't see any evidence of strain at all until it reaches its ultimate strength of 21,500 pounds, or about 9,800 kilograms. And then it breaks with practically no warning. It's strong, but it's also brittle. The sample failed with no sign it was about to go. The second sample we'll try has been tempered, so it should yield at a lower figure. We can see some sign of strain just before the piece fails. And sure enough, its ultimate strength to failure is only 19,400 pounds or 8,800 kilograms. The last sample is the one we've annealed. It should show about as much strength as an untreated piece, and we ought to be able to see it stretch before it comes apart. Watch here as strain begins to show. And the piece finally yields at 17,200 pounds, about 7,800 kilograms. You can see from all of this that just by controlled heating and cooling, we can change the properties of a metal to suit our exact needs. We can harden it to resist abrasion and to strengthen it. We can temper it to increase toughness and resist fatigue. And we can anneal it to make it easier to work and machine, and also to relieve stress caused by welding and fabricating. Next, we'll look at some of the reasons metal failures occur in the plant, and we'll see how these failures can be minimized. Before we continue, though, work through Section 5 in the text to make sure you've got a clear understanding of how heat treating metals works for you. As we've seen so far in this program, metals are tough substances. They can be made to withstand intense heat and tremendous forces. And metals can be treated and worked to give quite a variety of desirable properties. Still, machines do fail, and sometimes it's because metals fail to meet the demands we've placed on them. Some of these failures occur because the metals are overstressed, that is, their loads are just too great. Or it could be that the wrong metal was chosen in the first place. Other times, something goes wrong that causes the metal to be stressed far more than it was supposed to be. Loss of lubrication to a bearing is one example you might see in the plant. Lack of cooling to an engine is another instance of some outside event causing failure to an otherwise perfectly good component. When failures do occur, it's up to you to figure out what happened so a decision can be made as to how to prevent it from happening again. To be able to diagnose failures when they occur, you've got to know what kinds of failures there are and what causes them. Basically, there are 6 causes for metal failure in the plant. These are corrosion, erosion, heat, fatigue, ductile and brittle failures. Let's look at these one at a time. Corrosion and erosion of metals are pretty common causes of metal failures. Both of these involve loss of material. Corrosion is the eating away of material from chemical action. Exposure of metal to acids is one cause of corrosion. This pump shaft was attacked by acid being pumped through the component. The shaft is stainless steel, a corrosion-resistant alloy, but even this metal is subject to corrosion if it's exposed for too long. Erosion, on the other hand, is the wearing away of material by some physical action. An example of erosion often seen in a plant is the erosion that takes place in piping systems at elbows and T's. The fluid, either gas or liquid, will cause the metal the pipe is made of to be worn away where the fluid is forced to make a sudden change in the direction of the flow. Another example of erosion is this section of boiler tube wall. A soot blower that was blowing at too high a pressure eventually caused enough metal to erode away and the tubes burst open. Failure from heat can show up in a number of ways. In the example of boiler tube erosion we just saw, the higher temperatures inside the boiler accelerated the wearing away of the surface of the tubes. Temperatures that are too high and concentrated at a certain point will cause metals to weaken and can be a direct cause of metal failure. This can happen if a boiler's tubes go dry for even a short period. With nothing flowing through to soak up heat, the tubes themselves will melt. Fatigue occurs when stresses are repeated in a cyclic manner. Vibration in a piece of machinery can produce the kinds of stresses that eventually lead to fatigue failure. The stresses that cause fatigue failure may be much less than the ultimate strength of the material. The important thing to remember is that these stresses are repeated over a long period to cause failure. Ductile and brittle failures often occur because a metal was not treated correctly to get the properties it needed to do its job. A ductile failure that is often seen is the deforming of a bolt if it is over-tightened. It may not fail until you try to loosen it. Then it'll ring off at the first turn. Brittle failures also occur because treatment failed to temper the metal to regain toughness. Brittle failures may show up as fatigue failures, although single sudden shocks can cause a part to fail suddenly without any prior warning. In order to prevent metal failures, there are ways metal samples can be tested to assure that the metal has all the desired properties. Manufacturers and independent laboratories have destructive tests that cause a sample to fail in order to determine its ultimate strength. They can also determine hardness of sample pieces, as we've seen. In the plant, there are several means of non-destructive tests that can help us catch failures as they are about to occur. These methods are used when machinery is torn down for routine scheduled maintenance. Also, if a failure has occurred in a component, other parts may be checked by non-destructive testing to make sure they're safe to use when the machine is put back together. There are 4 methods of non-destructive testing that are often used in the plant. These 4 are magnetic particle, ultrasonic, radiographic, and liquid penetrant. The magnetic particle test, mag particle for short, can only be used on metals that can be magnetized, the ferrous metals. In the mag particle test, the entire part is magnetized and then sprinkled with very fine iron filings. A defect is indicated where the iron particles collect together. In ultrasonic testing, the second method, a high-frequency sound wave is sent through the part being tested. When the sound wave hits a flaw, it bounces back and shows up as a blip on a screen, much like a sonar scope. Radiographic testing is similar to taking an X-ray of someone to check for broken bones. The same kind of equipment is used and the same kind of precautions are necessary to protect personnel. The fourth method, the liquid penetrant test, is also called dye penetrant. The dye is put on the part to be tested and given time to accumulate in surface cracks. Then, a developer is used to draw the dye out to the surface and make the location of the flaw visible to the examiner. Any indication of a flaw in a part means that someone will have to decide whether it's relevant to the reliability of the part, and if it is, just what has to be done about it. That's where your knowledge of metals and their properties and how failures occur can be helpful. The more you know, the more accurately you can convey the information necessary to make the right decision. And if it's your job to decide, then you'll know with confidence that you're doing the right thing.